Hello, welcome to Morgan Labs. We have a spring pin cylinder problem. This is kind of like a thermal problem a little bit, but you're finding a spring constant. All right, so your spring and pin constrains a volume of compressed air. We'll say it's at 1 times 10 to the 5th pascals. You remove the pin and you allow the gas to expand. Additionally, we'll say that the height doubles after expansion, right? And then you maintain a constant temperature. Find the spring constant. We're going to neglect the weight of the piston. We're going to assume for P0, which is, you're just going to say P1, the initial pressure, P1. We assume no compression of the spring. Okay, to solve this, you're going to have a whole lot of equations. But so you won't get lost in the weeds, your focus, your target, little target symbol, is force equals Kx, Hooke's law. If you know the force on the spring at the end of the process and the deflection, X, you can find K. K is the spring constant. X is your displacement. But in order to find that, we need to know pressure times area equals force. But to know that, we need to figure out what the area is. And so we're given radius, so we can figure out the area. And then you have to figure out pressure. So it's at constant temperature. So that says we can use Boyle's law. That's what this is. PVs equal constant pressure times volume is a constant. That's Boyle's law. And then lastly, just use your volume equation to get the V2. And so this is all the information I believe you need to solve this problem and solve for K. Okay, so the last step, all we have to do is plug in the numbers for your equations. The hard part is figuring out which equations to use. And now we just have to make sure our units line up and we multiply everything correctly in our calculator. So we find the area, pi r squared, to be 0.00785. And then we use that to find the volume at V1, which is pi r squared times 0.1. That's your height over there. Okay. And we get 7.85 times 10 to the minus 4. V2, we use the same area because this is really cross-sectional area, right? It's like a piston. If I drew it in 3 dimensions, you know, I didn't draw the stem coming out, but we're neglecting the mass. So we don't have to really worry about that. But that's the area that you're dealing with, right? Kind of looking at it that way. So it's 0.00785 times 0.2, because V2 is this area, V1 is that area. Then we get 1.57 times 10 to the minus 3, and the units are cubic meters for both of these. Everything's in meters, right? Check your units, check your units. Everything in meters, pascals or newtons per meter, so your units are fine. Mostly, sometimes they'll just put things in centimeters, and you have to know how to convert that. But this is just pushing through the problem. Just basic knowledge you need to solve the problem. Okay, P2, you plug in your V1, your P1, and your V2. You get 5 times 10 to the 4th, and the units are pascals or newtons per meter, same thing. We have P2. Now we go down over here, and we finally get our final answer. Our spring constant is your pressure, which is your P2, times your area, divided by X, which would be this 0.2 wait, we gotta do something. X is our displacement. So we started off at 0.1, we ended up at 0.2. So the displacement is 0.2 minus 0.1, which is 0.1. So that's our displacement down there, okay? We're not just pulling this number, we're doing final minus initial to get our displacement. Very important. So we plug in the 0.1 and we get 3,925 newtons per meter. And that kind of makes sense. I probably should have tweaked the numbers a little bit, because usually your spring constant is something like in the hundreds, 200, 300, something like that. So, but anyway, this is the method on how to solve it. Hope you learned something. Like and subscribe. O'Morgan Labs.